All right. Well, good morning and good afternoon and good evening, everyone, depending on where you are. It is the top of the hour. This is Karen Maurikas, and I am hosting the OEM COG, the ICEA's OEM COG session for today. We have a speaker who is going to talk to us about second source manufacturing lessons from the Second World War. This sounds like it will be a very exciting session. But first, if I can advance my slides. Okay, this is who I am, Karen Maurikas. I'm from the Boeing Company. I am one of the original founders of the OEM COG. And for those of you who are new to this group, first of all, OEM COG stands for Original Equipment Manufacturers Cooperative Opportunities Group. It's a mouthful, we know, so we shorten it to OEM COG. And this group formed, we are ICEA members, and we formed because we are all OEMs. And we realized that we face different situations or challenges than some of the other participants in ICEA, such as the government, entities, these CETA contractors, tool providers. So sometimes OEMs we do things differently. And so this group formed to share some ideas and some best practices, to have discussions. We've had several presentations already. We are coming on for the end of our second year. Some of those presentations included things like we had digital engineering. In particular, that was the Boeing T-7A Red Hawk program. So of course, as your host, I'm from Boeing, so I have to mention that first. But we also had topics about trade studies and affordability. We heard a couple of times from the OSD CAPE. For instance, they were talking to us about inflation and escalation, things that OEMs need to be aware of. We've also heard about how to present our information and tell the story of what our data is actually showing us, how to interpret it and visualize it as well. And so just to give you an idea of who some of the OEMs are that are involved in this group, we've got BAE Systems, Ball Aerospace, the Boeing Company, Lockheed Martin, Raytheon Technologies, Huntington Ingalls, Northrop Grumman, and then there's some others too. Can't remember off the top of my head. So with that, I want to move into today's program. So our speaker today is Brent Johnstone from Lockheed Martin. So Brent is a is a Lockheed Martin Fellow. He has been with Lockheed Martin for about 34 years, and 31 of those years, he's been a cost estimator. He is located in their aeronautics division in Fort Worth. He's worked on F-16 and more recently F-35. He's got a Master's of Science from Texas A&M and the Bachelor of Arts from the University of Texas at Austin. Brent, for those of you who are familiar with ICEA, you probably have seen him around. He has presented many times at the ICEA annual workshop. He is also the Region 6 director, and Region 6 covers Texas, New Mexico, Oklahoma, Louisiana, and Arkansas, if I've got that correctly. Most of the chapters are located in Texas, or if not all of them. And then lastly, Brent was the winner of the best paper this year at the 2022 ICEA annual conference or workshop. So with that, I am going to turn the presentation or the microphone over to Brent, and he will talk to us about, hold on, let me get back to the right screen here. Oh, I went too far. Sorry. Okay, Brent is going to talk to us about, let me back up, second source manufacturing lessons learned from the Second World War. All right, Brent, I'm going to stop sharing and you can go ahead and start sharing.
All right, thank you, Karen. And thank you for coming in and listening today. I hope this is a useful presentation for you. All right, so as Karen said, my topic today is second source manufacturing, lessons from the Second World War. And to kind of tee up the subject a little bit, let's think a little bit about the dilemma that estimators have sometimes when they're asked to determine what's the impact of building the same product at two different manufacturing sites. You might ask, well, how does that situation come about? It can happen in a number of realms. You can have production at different facilities that are owned by the same company. A very good example of that's Boeing 787 that was produced simultaneously in Washington State and South Carolina for about 10 years. You've got situations with foreign co-production, and the history of foreign co-production goes back to the 1940s, and the co-producer may be responsible for anywhere between building a complete airplane. He might just build components, or he might be responsible for mate through delivery. But in each of these cases that I have outlined here, even going up to the F-35 today, you've got situations where, let's take the F-35, where wings are built at both Fort Worth and in Leonardo in Italy and in Israel. Again, on F-35, you've got situations where the mate through delivery is accomplished in Fort Worth, it's accomplished in Italy, and it's also accomplished in Japan, depending on the customer. You've also got situations like international cooperative ventures, everything from the Jaguar, the Eurofighter, Airbus commercial. And then finally, you've got situations where you've got competing companies that are producing the same items. That's a little less common in the aircraft industry. That's a little more common in missile production. There's a number of missiles that have been produced by multiple companies at the same time. Now, don't confuse what I'm just talking about with a typical work share arrangement, where two or more companies work together, but they don't make the same components. So let's take F-22. On the F-22 program, Boeing had responsibility for the wings and for the aft fuselage, but Lockheed didn't produce those products at the same time. Boeing had 100% responsibility for those units. So that's not the situation we're talking about here. We're talking about, again, where two suppliers or two OEMs are responsible for building the same product at different sites. So we can think a little bit about how that might play out from a learning perspective. What would we expect to see according to learning theory? So I've drawn up a hypothetical example here where you have a lead site that is responsible for the build of the aircraft or missile or what have you. And at the 150th unit, a second source breaks in. Now, you would expect that there's going to be some sort of learning loss that's associated with that. And in my example that I've drawn here, that second source, its first unit is equivalent to what it costs the lead to build at T-24. And if you want to work out the math, that's about a 20% learning loss, which is to say that 20% of the learning that had been accumulated by the time you'd built the first 150 units, 20% of that is lost as a part of the transfer. Or you can also look at it from that same calculation. You can look at it from the standpoint of unit setback. So moving from 151 to 24, that's an 84% setback in unit terms on the curve. And then each company from that point on goes on to build 350 airplanes, and the second source comes down the same curve, it's assumed, as the lead accomplished. And you can see here's the unit cost for each one of those. The last unit that the lead company builds, its unit 500, is about 2,700 hours. And the second site, its 350th unit is about a little under 3,000 hours. So two things to note from the example that I've drawn here. Number one is that the second source never converges with the lead site's cost. You never see those two lines intersect. And also coming from that is there's no point at which the lead site is always the cheaper of the two units, the two companies. Now, unfortunately, this is a very nice theoretical example, but there's a lot of situations here that are kind of unexplained. And one of them is, well, how much learning would we expect to transfer between the lead site to the second source? I've made an assumption here, but I could be right, I could be wrong. There's not a lot of guidance that learning curve theory gives you in terms of how to calculate what that setback might be. What kind of learning curve slope would we anticipate that the second source? Again, I made an assumption here that it was going to be the same as what the lead site experienced, but there's no guarantee that that's going to happen. It could be better, it could be worse. Is it possible for the second site, for its curve to actually intersect, to converge with the lead site? An example I've drawn, that didn't happen, but again, it could happen. And finally, is it possible for the second source to actually have a lower cost than the lead site? So if we advance our ideas a little bit here, and let's say that we play around with the numbers and we say, oh, well, I think that the second source site would have a 76% learning curve going forward, as opposed to the lead site's 80%. Well, now you've got a situation where now you have a point of cost convergence. So that is to say that the second source actually intersects the lead source's learning curve. But even carrying it out even further, you actually see at the end that the second source cost is actually below the lead site's. So again, the lead site had 2,700 hours at its 500th unit, but the second site was able to produce at about 2,400 hours. So, okay, that's all very interesting. So much for assumptions. What guidance is there out there for the estimator? How does he know what to do? How does he know what kind of assumptions to make in terms of setback? What kind of assumptions he needs to make in terms of learning curve? Not a lot of guidance out there for people trying to make those decisions. So let's kind of step back a minute and think about this in terms of 4 propositions that we want to test. Okay. So proposition number 1 says, we're going to transfer some degree of learning to the second source. It's not going to start back at number 1, but not all of that learning is going to be transferred. Okay. Number 2, let's state that we think a strong effort by the lead to go promote technology transfer should result in less learning loss. Okay, that seems a reasonable assumption. Third, let's assume that the second source is not going to fully converge to the lead's learning curve. That is to say that those 2 learning curves are not going to intersect. And then fourthly, let's assume that the second source is not going to be able to produce at a lower cost than the lead, that the co-producer's best hours per pound are going to be higher than the lead company's best hours per pound. So these are our 4 propositions, our 4 assumptions. Is there a public domain data set out there that we can use to go test those assumptions? There's a lot of data out there, but unfortunately, it's closely held proprietary information. We have it, Boeing has it, Northrop has it. Lots of people have that kind of data, but it's not really available, obviously, to go share. But there is a data set out there which is public domain, and that's been used for a variety of learning curve studies over the years. And that's a document that's called the Source Book of World War II Basic Data. And what that book does is it provides hours per unit and hours per pound data per month by model and by company. And as part of that, there's a number of examples where the same aircraft model was built at different sites. Now, you may say, well, gee, that's kind of old data, right? And it is, but I think it can still provide some valuable insights into learning transfer and to learning curve performance. And to make you feel better, at the end of this this presentation, I'm going to compare the results at a high level to modern day examples to see if the conclusions that we drew from the World War II data are still valid. So let's step back in the time machine. Let's go back to the age of our grandparents or great-grandparents, depending on how young or old you are, and think about the aircraft industry prior to World War II. So the U.S. aircraft industry before World War II was not in any way, shape, or form designed for mass production. And aircraft were made in small quantities in an artisan job shop environment. In fact, the production line that we think of today in aircraft didn't exist at all. You essentially built aircraft in one spot on the factory floor in its entirety. So think about how you'd build an airplane if you're going to do it in your own garage, and you're not terribly far off the processes and the methodologies that were used in the late 1930s. And as a result, the U.S. aircraft industry was pretty small. In 1938, it employed 36,000 people, which was less than the knit hosiery industry in the United States. So think of men's socks and women's hose. And that gives you an idea of how small a contributor the aircraft industry was at that point to the United States economy. When World War II came about, of course, as you know, the war in Europe began in 1939. The United States did not enter the war until 2 years later. But even by 1940, it was apparent that the United States was likely to be drawn into the war, and efforts were made to start preparing the U.S. for that effort. So in May 1940, coincidentally, the same day that German forces crossed the Belgian and Dutch borders on their eventual drive to Paris, Franklin Roosevelt addressed Congress, and he issued a challenge and said, and told Congress that he wanted to see the United States geared up to the ability to turn out at least 50,000 aircraft a year. And that was an extremely ambitious target, given the fact that in the prior year, 1939, the United States had delivered less than 1,000 military aircraft of any sort, be it fighters, bombers, cargo planes, what have you. So to get to 50,000 aircraft seemed like an extremely daunting task. So the United States began to make preparations for that and decide how to best employ its industrial resources to do that. And one of the plans that they came up with was that there would need to be a substantial expansion of the country's aircraft manufacturing facilities. And also they came up with a plan that said that it would be best if the production of those aircraft were dispersed among multiple companies if possible, so that multiple companies would be making the same aircraft. So if you look at, let's say, heavy bombers, for instance, which was a high priority of the Air Force at the time. When the war began, there were essentially two major models in production, the B-17 and the B-24. B-17 was produced in Boeing, Seattle. The B-24 was produced in San Diego by Consolidated Vultee. Later in the war, the B-29 came on. That was a Boeing aircraft. It was initially produced in Wichita, Kansas. Again, like I said, it was one of the high priorities of the government to increase that capacity as rapidly as possible. So on for the B-17, at the same time Boeing was producing those aircraft in Seattle, Lockheed was given a contract to produce those aircraft at its facility in Burbank, California. And at the same time, Douglas Aircraft was given a contract to go produce them at its Long Beach facility. For the B-24, a number of new facilities were opened up. So among them were Consolidated's plant opened a new plant in Fort Worth, Texas, which is actually where I'm addressing you today. Only now it's under the Lockheed name. North American built a facility in Dallas, technically Grand Prairie, as the people in Dallas County will tell you. Douglas built a facility in Tulsa, Oklahoma, and the Ford Motor Company. There was a big push by the government to try to involve the automotive company as much as possible in the war effort. The Ford Motor Company built a plant in Willow Run, Michigan to produce B-24s. And then finally, for the B-29, again, facilities were, a new facility was built by Boeing in Renton, Washington. Martin built a facility in Omaha. and Bell built a facility in Marietta, Georgia for the B-29. If you look at the map, like I said, you will recognize some of these facilities are still in existence: Renton, Fort Worth, Marietta. So a lot of these facilities, or at least some of these facilities, still exist even today. So let's talk about some of these aircraft and some of the experience that these companies had as they were trying to produce them at the same time. So let's start with the B-17. So the lead site for the B-17 was Boeing Seattle. And as I said, additional production was done at Lockheed in Burbank and by Douglas in Long Beach. Over the course of the war, over 12,000 B-17s were built. That's a pretty astonishing number if you stop and think about it. The F-16, which is considered to be a high rate production program, we built over 4,000 of those, but that first aircraft was delivered in 1976. So in the course of, we have not, even on the F-16 in its heyday, when we were delivering 200 aircraft a year, never approached anything like the rates that were accomplished during the war. For those of you who are curious about the matter, the average flyaway cost of a B-17 in then-year dollars was about $204,000 an aircraft. That'd be about $3.2 million in today's economics. So when we step back and we look at the performance on the B-17, if we look at it from an hours per pound perspective, what I've done here is I've plotted the three sites: Seattle, Long Beach, Burbank, and I've plotted them in this particular view at the lead site's cumulative quantities. So you can see Seattle, actually even prior to the war, was producing B-17s at a low rate. So we're missing a little bit of data at the very front end. Somewhere after Seattle had built about 1,000 B-17s, the Long Beach facility began to produce B-17s, and after about 1,500 units or so, Burbank began producing them. So one of the things that's immediately apparent when you look at this data is you can see that Burbank and Long Beach converged to Seattle's learning curve. They were able to intersect Seattle's performance on an hours per pound basis. Now, the next view that I have is exactly the same data. I've just changed the perspective of it a little bit. And you can see this now from the perspective of treating each company as if they were independent. So the break-in unit of each site is plotted as T1. It's the same data, it's the same hours per pound, just a different view of it. And what's apparent when you look at this is you can see that Burbank and Long Beach were able to produce at a lower hours per pound than Seattle, which is not exactly what, as we discussed earlier, what learning curve theory would lead you to think was possible. So if we step back and look at the data and look at the performance of the three companies, it's very apparent that there were very low rates of learning loss when the build responsibility was transferred, or those new companies were brought in on the build. So in the case of Burbank, there was about 2% learning loss, and there was about 12% learning loss for Long Beach. Now, the immediate question is, well, how did that happen? Well, if you go back and you look at the history and you look at the records that are associated with it, you'll discover that there was a very high level of cross-company coordination. There was a committee, the so-called BDV committee, Boeing, Douglas, and Vega. The Lockheed branch that was building the aircraft was known as Vega Aircraft. That committee got together, and their primary responsibility was to try to make the transition and to build between the three companies as smooth as possible. So they did things like they coordinated their material purchases, their master production schedules, the engineering releases, inspection criteria, production lessons learned. They put a very strong effort into what I would call technology transfer. And consequently, Not only were there low rates of learning loss, but both Long Beach and Burbank were able to sustain relatively steep learning curves, 55% for Burbank, 68% for Long Beach, relative to Seattle. So the program was very successful in terms of accomplishing that learning transfer. All right, let's move on to the B-24. So the B-24, the lead site was Consolidated Vultee in San Diego. And there were additional sites by Consolidated in Fort Worth, by Ford at Willow Run, Douglas in Tulsa, and North American in Dallas. Over the course of the war, there were about 18,000 aircraft that were produced, and the average flyaway cost relatively comparable to the B-17, $216,000 a unit is about $3.4 million in current dollars. So if we look at the B-24 performance on an hours per pound basis, we see some really startling differences in the performance of the contractors who did it. You can see, again, we're missing some of that early San Diego data, but we can extrapolate what their performance would be on that curve for those early units. You can see from the standpoint of Willow Run, for instance, there was a very, very large setback. And we'll talk about some of the reasons why that happened. Also, there were some large setbacks in terms for Tulsa and for Dallas, less so for Fort Worth. But you'll also see that Fort Worth, Willow Run, Tulsa, and Dallas all were capable of converging to San Diego's learning curve before the end of the program. Now, again, this is our view. Everything's viewed from same data. It's just viewed from the perspective each company's plotted as T1. You're able to see here that Willow Run was actually able to produce at a lower hours per pound than the lead site. The other sites came very close, but they didn't exceed. They didn't go below San Diego's hours per pound performance, but Willow Run was able to do that. So again, let's talk about Willow Run for a minute, because it's a really interesting example. It's kind of illustrates the extreme case of learning transfer. So Henry Ford decided that was very anxious to get into the aircraft production industry, and he sent his right-hand man, a gentleman by the name of Charlie Sorensen, to San Diego to look at the Consolidated's facility. And as an automotive man, Charlie Sorensen was really disappointed in what he saw. You can read the quote that I've an excerpt from his memoirs, but he talked about that in his mind, the B-24, the way it was being built in San Diego, he referred to it as a custom-made plane put together as a tailor would cut and fit a suit of clothes. He was, as I said, disappointed, and when he was asked about it, he expressed his concern to the Consolidated management. And they asked him, well, Charlie, if you were in charge, how would you do it? And he says, well, I'll give you an answer tomorrow. So he went back to his hotel room and essentially pulled an all-nighter. And when he came back the next day, he had drawn up plans for a brand new production facility, organized on the principles of mass production as the Detroit auto industry had engineered it. And that was the plan that he took back to Henry Ford and sold Henry Ford on the necessary investment it would take to go build that facility. So essentially, Ford Motor Company just completely rejected Consolidated's assembly approach. They built a new facility based, as I said, on the automotive mass production. It's enormous investment in tooling, about the equivalent of about $1 billion to $1.5 billion in today's money. And the plan for it was that it was going to be capable of producing a B-24 every hour. So if you do the math, 24 hours a day, 7 days a week, that would be about 700 aircraft a month. Ford ran into big problems from almost the beginning. And the opening problem was that they really couldn't reconcile Consolidated's drawings to what was really required to build the part on the shop floor. So Consolidated had drawings, but there was a lot of tribal knowledge that wasn't captured on those drawings in terms of how to build the airplane. And so Ford deemed that to be inadequate. So eventually they redrew 30,000 engineering drawings in the process. At the same time, there were thousands of design changes that were coming in from the field. Ford struggled with that. And in the end, they built 21,000 jigs and tools, but they scrapped 10,000 of them before they were done. So you can see that there was essentially, in the end, there was absolutely no learning gain experience. So Ford's first unit was actually higher than Consolidated's first unit. But once those initial problems were overcome, Ford was able to become the most effective B-24 supplier. So the approach of approaching it like an automobile, using those principles, actually in the end did bear fruit. Now, Ford never did produce 700 aircraft a month. Eventually it produced 400 aircraft a month, but it was able to do so at a lower hours per pound value than any other B-24 site. All right, let's again talk about the B-24 lineup, the builders, and look at how they did. There's a very, very wide range of learning loss, as little as 3% for Fort Worth, as high as over 100% for Willow Run. There was no coordinating committee like there was on B-17 and later on B-29. In the case of Fort Worth, the advantage that it had was it was the same company, right? It was Consolidated Aircraft. And San Diego was able to provide a cadre of engineers and management to the new sister plant at Fort Worth. So there was a lot of learning transfer that was accomplished there. Willow Run, we've already discussed what their issues were. Dallas had an issue, ironically, with drawings that were provided by Willow Run. And there were also issues with communication of engineering changes. So that's why Dallas had a fairly large learning loss that it experienced. But you're able to see too that you had steeper learning curves for those co-producers, 70 to 73% slopes relative to San Diego, which enabled them to converge with San Diego's performance, and in the case of Willow Run, actually go below it. All right, let's move to the B-29. So the B-29, the Superfortress, was considered to be the ultimate bomber. It had very long range. It was ideal for the Pacific theater. Very high priority in the war effort. So the lead site was Wichita, Boeing Wichita. Additional sites at Bell in Marietta, Boeing in Renton, and Martin Aircraft in Omaha. There were about 3,900 aircraft that were produced. The average flyaway cost substantially higher than the other two aircraft. It was about the equivalent of about a little under $10 million a unit in today's dollars. The cost of the total program at the time was $3 billion. Today, that'd be about $45 billion. Again, let's step back. Let's look at the performance in terms of it, how they did on the lead site. Marietta came into the program relatively early with about unit 75. Renton came in a little bit after Wichita had built about 100 units. Omaha later, a little closer to 400 or 500 units had been built. Renton and Omaha were able to converge with Wichita's learning curve. Marietta, as you can see, briefly converged and then stayed above. This is the view with each site treated as if it were its first unit were T1. That makes it pretty clear. You can see that no site was able to produce at a lower hours per pound than Wichita. So when you look at the performance of the companies, again, you can see a good range in terms of the learning loss, as little as 14% for Renton, up to 49% for Marietta. One of the things that's interesting is that, similar to the B-17, you had a cross-company coordination committee. But what complicated that was that you had 5 other companies, Chrysler, Hudson, Goodyear, McDonald, and Republic, that were providing components and sub-assemblies at the same time. And you'll notice of those, you probably don't recognize the name Hudson. That was an automobile company. Goodyear, of course, is Goodyear Tire. So out of that list, only two of those, McDonnell and Republic, were true aircraft manufacturers prior to the war. So at the same time, you've got the sites you've got multiple sites producing the airplane. You've got a number of feeder plants that are providing parts and components. So the B-29 was considered to be the most complex joint production undertaking of the war. And consequently, because of that complexity of the supply chain, it's probably not really surprising that those companies, Bell, Boeing, and Martin, had slightly flatter curves relative to Wichita. They weren't really able to, didn't see some of those startling curves that we saw in the case of the B-17, for instance. So when we look at all the aircraft and we look at all the sites, what can we conclude out of this? Well, on average, those second sources experienced a 36% learning loss. And 8 out of the 9 were able to converge with the lead site's learning curve at one point or another. And 3 out of those 9 were able to produce at a lower hours per pound than the lead site. Now, the caveat to this is, of course, that these co-producers, they all experienced exceptionally high production runs. So you had 500 to 8,000 aircraft in some cases that they were producing. So certainly if you were going to try to think about this data and use it, and you had a co-producer that was going to produce 50 aircraft, clearly you're probably not going to see a company capable of getting to a lower hours per pound than the lead side. So I promised you earlier that we wouldn't just look at World War II data, we'd look at some contemporary data, and that's what we're going to do. Now, for proprietary reasons, I can't identify what these specific case studies are. I can tell you that they're all within the last 30 years. But if we step back and we look at those, on average, what the second source, they experienced a 38% learning loss, which compares remarkably with 36% for the World War II case. So very, very close to one another. The modern day data has a narrower range of learning loss, so 23 to 56%. If you remember, in the case of the World War II data, it was probably extremes were 2% to 106% learning loss. I would attribute that to these programs had all a very strong emphasis being put on successful technology transfer. So in terms of transferring data, training, on-site management, assistance teams, furnishing startup parts, there was a lot of effort put to make sure that the co-producer was going to be successful and to maximize the amount of learning transfer from the lead to the second source. And consequently, the second source was able to converge to the lead in about half of the cases, more than half. And in some of those cases, the second source was able to provide a lower hours per unit than the lead. So what does that mean for our 4 propositions that we talked about at the beginning? So to kind of revisit our propositions, proposition number 1 said that, well, we would expect to see some learning transfer, but not all the learning would be transferred. And I think that's confirmed by what we see from the World War II data, that there was on average about a 30% average learning loss. And only in the one case for Willow Run did you see a complete setback to T1, and for a very good reason, that Ford ultimately rejected Consolidated's approach and decided to go strictly on its own. Second proposition is that a strong effort by the lead to go promote technology transfer should result in less learning. I think that the World War II data shows that the ability to transfer engineering data and manufacturing process is really a critical factor in determining the degree of learning loss. In cases where we were able, the companies were able to, the lead was able to make that transfer, there was a significant reduction in the amount of learning loss. So from an estimator standpoint in a contemporary environment, that's something that you have to look at very closely, is to try to understand what is the plan for technology transfer. What is the plan to get the second source online as quickly as possible, and transfer that engineering and that manufacturing knowledge. The third proposition is the second source is not going to fully converge to the lead's learning curve, that the two won't intersect. However, from the World War II data, we were able to see that in more cases than not, the second source was able to converge if they had sufficient production quantities. And again, that's a big caveat. Again, if the co-producer is producing very small quantities, you're not going to see that. And finally, proposition number 4 says that the second source won't be able to produce at a lower cost than the lead. And data shows that, in fact, it is possible for the second source to produce at a lower quantity if there's a steep enough learning curve and there's sufficient quantities to do so. So that's certainly not a guarantee. And if one were putting together wanted to be conservative in the estimate, I wouldn't make that assumption that that was going to happen. But the data shows that it is possible. It can be done in the right circumstances. So that is the end of my presentation today. I'm happy to take any questions that you might have on this subject, and I'll hand it back over to Karen.
Okay, well, thank you, Brent. I'm going to share my screen. Let's see this one. And bring this back up. So I heard Brent give this presentation at the annual workshop in May in Pittsburgh. And at the time, thought it was very interesting, great presentation. I have the exact same impression today. Even though I heard it before, I found it very fascinating. So thank you, Brent.
Well, thank you, Karen. And you know, I did give a nice shout out to the Boeing company in this. So, you know,
yes,
free advertising.
I appreciate that. And actually, I'm thinking, you know, there's some people at the Boeing company who could probably learn a few lessons from this presentation. So I'm going to make sure that they get a chance to see it if they're not on the call. So we are going to questions and answers, a period. So if you do have questions for Brent, you can put them in the chat. Megan will be monitoring that. And Megan may be able to give you the option of asking your question live. I'm not sure if we have that capability, but if not, please put your questions in the chat or in the Q&A for Megan. And while you are doing that, I wanted to comment on the Willow Run, specifically the Willow Run case, Ford Willow Run case, where they found that the drawings were not sufficient. They could not figure out how to make that work with their production line. And that just goes back to one of the other points that Brent brought up about how the importance of good documentation and good communication. So if you don't have your processes documented, well documented, and if you don't share that information with other people in your company or other companies that are working with you on this, there are going to be problems. So, you know, it's really important to make sure that you're sharing good information.
I just add on to that to try to tie that back to some of the other topics we've discussed in the past. You know, one of the, I think the big thrusts of the digital transformation is to have better process, a better communication of lessons learned, and the back knowledge, if you will, on how things get built that aren't necessarily captured in a paper drawing, right? I know that there's been experiments with videotaping processes so that the mechanic can actually see how to perform a task, something that's obviously not captured in a paper drawing, right? So I think that's one of the big thrusts on digital engineering ultimately, is to try to get a better handoff and to do a better job of documenting that. And so, because not everything, you can't get everything on a two-dimensional piece of paper. So I think that obviously that, as you pointed, you know, that you pointed out on the Willow Run case, that's pretty important if you want to have a successful transfer of learning to either both in the second site or among within a facility, because you always got new people coming in and you need to transfer that.
Right. So Megan, do we have anything in the Q&A section?
We do indeed. The first question was, will the slides and video be able to be available for everyone to view? Again, yes, by tomorrow at lunchtime, the video should be up on iceaonline.com/OEMcog. If those of you who are very excited and want to start looking at the slides again before that, you can go to the Pittsburgh page. I think it's iceaonline.com/PIT2022 and go to the sessions, and you'll be able to download Brent's slides and his narrative white paper from there as well. The second question we got in says, understanding the need for confidentiality for the modern day example, how many companies were the comparisons spread across?
They were all internal to Lockheed Martin or Lockheed Martin Legacy, which covers a lot of territory these days with the consolidation. But they were all Lockheed internal examples of one form or another.
All right. Karen, why don't we, for everybody on the line, give you a few more minutes to ask questions. Oh, well, that's all it took. All right. Interesting data. Appreciate you sharing. Do you think the key to the improvement is high levels of cooperation between builders? Is any of the data based on competitors?
Well, like I said, on the contemporary example, that is all Lockheed internal experience. Obviously, in the case of the World War II data, those were companies that were competing against each other. But obviously, in a wartime environment, it's a little different. You know, everybody's got a single-minded task to go, defeat for the United States to emerge victorious. So there were a lot of that was put aside, that kind of that rivalry between the aircraft companies. So that was obviously beneficial. Yes, I do think that high levels of cooperation is very important between builders when you've got a second source situation, because if you don't have that, then you're basically condemning the second site to rediscovering and making all the same mistakes that the lead site did and finding out for themselves. And that has a lot of negative aspects. Not only, are costs going to be higher, but probably your schedule is going to suffer, probably your quality is going to suffer as well. And it's going to produce some really negative impacts, potentially on the lead sites line. For instance, if the second source is responsible for building a subcomponent, let's say a wing, and that wing comes in and it's poor quality and it's late, then that's going to have some pretty serious downstream impacts. So there's a high incentive, I think, for lead companies, especially in today's environment, to try to transfer knowledge and to do as good a job as possible in transferring that information. But sometimes that's not very easy. I mean, like I said, we talked earlier about not everything can be communicated in a 2D drawing. Sometimes you've got language barriers, right? You may be, in the case of F-35, you're taking planning in English and you've got to go give that to, an Italian workforce or a Japanese workforce. And sometimes that stuff doesn't necessarily translate very easily. So there's always those kinds of barriers, and it's pretty critical to try to work through those as best you can, because otherwise the consequences can be not so good.
All right, this next question came in with a preface that it might have been answered already, with apologies. Was there any analysis into what contributed most to the learning loss? Was it improvement in labor skills and experience, or manufacturing tools, factory layout, or other things?
I wasn't able, based on the data that I had, to get down to that level. There has been some analysis that has been done, and in particular, there was a study done about the level of improvement at the Boeing's B-17, B-17 build in Seattle. and what were some of the factors that contributed to that. And that particular study came up with some surprising conclusion. I'm not really persuaded by it. They really felt it was more of the capital expenditures that Boeing made that made the contribution to coming down the curve. I'm not 100% sure I really buy that based on what the evidence that was presented in that paper, but that's still a big, that kind of goes back to the broader mystery, if you will, about why does the learning curve happen? What are the main contributors? And there really is not there's not a universal understanding of what elements are more important than others. That's still up for debate. So I didn't really try to touch that in this paper, didn't really have the data necessarily to go do that. That would be an interesting follow-up. But I don't know that I have a strong opinion on what those elements were, which element was more important than the other.
All right. So let's give everybody another minute or two to throw in their questions. Why don't we go through the slides to give some folks some time. So coming up also, is that next week? Goodness gracious, next week. September 21st at noon is the 2022 all-member virtual meeting. This is where you'll be hearing from ICEA Executive Committee, President, Vice President, and yours truly about the state of the association and what we're doing, what we're up to, what we're working on. When you RSVP, you'll be able to send us questions in advance, the things that you're thinking about and want us to cover. So hope to hear and see all of you guys on that.
And just a clarification, that's noontime Eastern.
Oh.
So if you're on the West Coast, that would be a little bit earlier.
Yes.
We don't want you to miss it.
Brent, do you want to touch on this one?
Yeah. So Region 6, which as Karen described is Texas and the adjoining states. Region 6 will be holding a webinar next week, next Thursday, and that'll be 12 o'clock noon Central Time on affordability engineering and its impact. So our speaker is going to be a gentleman by the name of Javier Provencio. Javier is an affordability engineer at Lockheed Martin Missiles and Fire Control. He's also doing some work for RMS, which is the Rotary Mission Systems division. And Javier is going to talk about his experiences on affordability engineering, what some of the roadblocks are, how to overcome those roadblocks. So it should be an interesting presentation, and it's open to everybody. It's not just Region 6. Anybody who has any interest, even if you're not a member of ICEA, it's open. So all you have to do is register, and you'll be good.
And this is actually a topic that's of interest to the OEM COG. So if there are any COGers out there who are interested in affordability, I'm planning on attending. So I think it'll be a pretty interesting conversation. And then the next one is a webinar from the Southern California chapter about a week later. So now September 28th at 11:30 Pacific. We will be hearing from Brittany Clayton, who's from the RAND Corporation, and she will be talking about digital engineering implications on weapon system costs. And then also not listed here, but if you are from the Southern California area or a member of the Southern California chapter, we will be talking about the upcoming elections, the board for the next 2 years, the board of the Southern California chapter. So if you are at all interested in getting more involved in the Southern California chapter, you could reach out to me or definitely attend this webinar and you will hear more about it. And back to you, Megan.
Something for everyone to keep on their radars. If you are not already an ICEA member, or you are and you want to keep on being, we're raising our dues on October 1st. So get in while the getting's good. That'll be until September 30th. You can renew or extend your membership at the current rates until the end of the day, September 30th. They'll automatically switch over at midnight Eastern from the 30th to the 1st. So do it when you can. And even if your membership isn't due for a while, if you know you're going to want it for another year, go ahead and buy it now, and you can enjoy the current rates. And then last, I think.
And before we go on, I did see a question come in just to me, but I am going to announce it to everyone. So as we were talking about I mentioned the OEM COG and I called us COGers. The question was, are we COGers now? So that's something that the group can decide. Do we want to be called COGers? All right, and Megan.
I'm sorry, I'm hung up on the COGers thing. All right, let's go, COG. Then the next big is the call for papers. Those are due November 1st. So get your gears turning. This is to get you on the schedule in San Antonio. You only have to provide 75 words at this time. Your first draft of your presentation or your narrative paper, if you want to write one, isn't due until February. But this is what gets our review committee to see you and see what you want to present and decide who gets first cut at presenting. All of these things, everything we've promoted and more, you can get the links to RSVP to them or read more information about them. If you go to the main page, ICEAonline.com, there's a rotating series of ads and pictures on the front page that has links for all this stuff. So that's where you can go, but if you don't write that down now, you can get to it from the front page, and as well as the Region 6, Southern California, and other upcoming events. And it looks like the questions are starting to dwindle. So with 4 minutes left to go, I say, Karen and Brent, why don't you guys close us out? Let everybody have, oh yes. Go ahead, Karen, take this and land the bird, if that's appropriate.
All right, so for I'll say for the COGers or anyone associated with the OEM COG, if you have specific topics that you would like this group to consider to discuss, either in a small group, as a working group, or as a webinar, please reach out to us. Yeah, you can email Megan at ICEA@ICEAonline.org, or if you happen to know a specific person in the OEM COG group, you can go ahead and reach out to any of us. We'd love to hear what you're interested in so that we can make sure that this venue is applicable and of value to all of you. And I think that is the last one.
Awesome. Thanks, Karen. Thanks again, Brent. Thanks everybody for joining us today. We're gonna call it, give you back a few minutes of your life before you have to get your next meetings. So thank you, everybody. Have a great rest of your day.